So as I promised before, we're now going to take a look at more complicated rational functions, ones that we can't just use basic transformations to graph. And the idea is that we're going to use this 7-step process to help us graph them. So first going to go over the 7 steps with you, make sure you understand each one of them, and then we're going to switch boards and we're going to do a few examples using each one of these 7 steps to help us graph more complicated rational functions. Now the first thing we always want to do to graph rational functions is to make sure we factor it completely. In factoring it completely, that will help us to figure out what the zeros of the numerator are, the zeros of the denominator, and that will help us to be able to determine what some intercepts are and what some vertical asymptotes are pretty quickly. So the first thing we always want to do, if it's factorable, is to factor it completely. Now, when we're done factoring it, we're going to start gathering some information about some ordered pairs that are on our graph. So 2 pieces of information, and the order in which we do 2 and 3 is entirely unimportant. You can pick and choose. I just wanted to list some type of order. But next what we want to do is we want to find if the graph has any y-intercepts or if the graph has any x-intercepts. And as we talked about before, the definition of the y-intercept is when x equals 0. So you're going to look at the function, you're going to substitute 0 in anytime there's an x, and it will spit out a function for you, and that represents the y value. So what we're doing is we're getting a few ordered pairs that are on our graph. So when we're done with the y-intercepts, then we're going to find the x-intercepts. And the definition of the x-intercepts are when our y value equals 0, but it turns out that it's the same thing as finding the zeros of the numerator. So we're going to factor, we're going to find the y-intercepts, we're going to substitute 0 in for x, and then we're going to find the x-intercepts, which means we're going to substitute, we're going to look for any zeros of the numerator. Now for the 4th step, now we're going to look for any vertical asymptotes. And as we said before, in the graph of the function f of x equals 1 over x, that the vertical asymptotes are the domain restrictions. So anytime we have a restriction on the domain, any type of zeros in the denominator, then we have a vertical asymptote. And we're going to represent them by putting dashed vertical lines. I wrote horizontal here, sorry, but I meant vertical. We're going to represent them by putting dashed vertical lines in whatever our vertical asymptotes are. So if we have a vertical asymptote at x equals 3, we're going to draw a dashed line at x equals 3. Or if we have a vertical asymptote at x equals 7, we're going to draw a dashed line at 7. Now remember, the vertical asymptotes, our graphs will never cross over them. So they're giving us a boundary for the graph. They're telling us that the graph's going to come super close to the asymptotes, but it's never going to cross over it. So it's helping us to, again, gather together some information for what our graph will look like. Now the next step we're going to do, and this is our 5th step, is to find the horizontal asymptotes. And this one involves a little bit more thought. Now remember, the horizontal asymptotes are a horizontal line. Our graphs can cross over the horizontal asymptotes, but they give our graphs kind of a magnet or a road for our function to follow. And I like to think of it like our graphs are drawn to them, so they're magnetic. And here's the way we're going to handle the horizontal asymptotes. And there's 3 different cases we have to think about. And we're going to use the degree of the numerator and the degree of the denominator to compare the horizontal asymptotes. So if the degree of the numerator is smaller than the degree of the denominator, so you look at the degree of the numerator, you look at the degree of the denominator. If the degree of the numerator is smaller than the denominator, that means we're going to have a horizontal asymptote at y equals 0. So done. Degree of the numerator is smaller than the degree of the denominator, we have a horizontal asymptote at 0. Now let's look at another case. What happens if the degrees are the same? So what happens if we have, let's say, a 2nd degree polynomial in the numerator and in the denominator? If the degrees of the numerator and denominator are the same, then we're going to have a horizontal asymptote at the line y equals a over b. A is the leading coefficient of the numerator, and b is the leading coefficient of the denominator. So we're going to think of this as being a ratio. You ask yourself, what's the leading coefficient of the numerator? Let's say it's 3x squared. What's the leading coefficient of the denominator? Let's say it's 5x squared. And so that means we're going to have a horizontal asymptote at y equals 3 over 5. And as we did over there with the vertical asymptote, we're going to draw a dashed horizontal line to represent this. Let me just put this in here. A dashed horizontal line. Now keep in mind, once again, that we can cross over horizontal asymptotes. We cannot cross over vertical asymptotes, and that's going to become important in a few minutes. The last case we have is what happens if the degree of the numerator is larger than the degree of the denominator. Well, then we have something that we call a slant asymptote. And we're not going to worry about that in this class. It's just a case that we kind of ignore. But if it does happen, you would divide the numerator by the denominator. Whatever the remainder is, that's what the asymptote will look like. But again, we're not going to worry about that in the scope of this class. We're really going to focus on these first two. What happens if the degree of the numerator is less than the degree of the denominator? What happens if they're equal? We're going to focus on these first two. Okay, so far we did the following. So far we factored, we found the x-intercepts and the y-intercepts, we found the vertical asymptotes and the horizontal asymptotes. So what we're looking at right now is a graph with some points on it and a bunch of dashed lines on it to represent the asymptote. So the important part is the sixth step, which is to create a chart that approaches the vertical asymptotes from the left and the right. Now the way I like to think about the sixth step is the following. Remember that we can't cross over the vertical asymptote. So picture that there's an infinite wall in front of you. That means that our graphs have to do one of two things. As you get closer and closer to an infinite wall, you can either climb up the wall or you can climb down the wall. So what the vertical asymptotes are going to do is they're going to tell us that at this point the graph can't cross over it, but in either direction we either have to go up or down. Same thing coming from this direction, we either have to go up or down, because the whole domain of these graphs will be covered except for wherever we have some asymptotes. So we're going to use this chart over here to help us to determine if our y values are going to approach positive infinity, if we're going to climb up the infinite wall, or if our y values are going to go down to infinity, if our y values are going to approach negative infinity, if they're going to go down the infinite wall. And we're going to do an example or two of this in a minute. Then what we're going to do when we're finished creating this chart is we're going to put all of these steps together and we're going to talk about what the graph of the function will look like. But don't forget these 7 steps. Factor, y-intercept, x-intercept, vertical asymptote, horizontal asymptote, and then we have the approaching the vertical asymptote chart. These 6 steps will help us to figure out what the graph of a rational function will look like.